project is for my thesis, so I should be finishing up in December, and then I'll just get back into the actual content again. I'm going to be talking about the work I've done regarding the effects of thermomechanical pretreatment on abnormal ossified grain growth during carburization. So I'm going to give you a little background on that topic, talk about the alloys that were used in this work and their initial processing conditions, the experimental conditions they were subjected to, the results we've obtained, and the conclusions we've drawn from them. So, for anybody unfamiliar with abnormal grain growth, it's where there is a bimodal grain growth in a microstructure. So here, it's not a steel, but it's nickel, but it does a good job of illustrating both how temperature and cold reduction can affect abnormal grain growth. So it ranges from 0 to 9%, and temperature ranges from 700 to 800 C. And you can see at lower reductions that you have abnormal grains highlighted. You can see the highlighted abnormal grains, and after you apply some percentage of cold reduction, those grains start to emerge at lower temperature ranges. So this is kind of similar to the effect that we're investigating in the steel. So the issue with this abnormal grain growth is that carburized parts, which undergo more and more cold forging operations prior to that carburization, can have the temperature range where that abnormal grain growth occurs affected by that work. And this particularly negatively affects fatigue performance, having these large abnormal grains present in the microstructure. So as far as the mechanism for abnormal grain growth, it can likely be attributed to the growth of precipitates according to the Zenner Ring equation. So when you have precipitates formed in the microstructure that begin to coarsen and dissolve, that is when abnormal grain growth ends and abnormal grain growth typically initiates. And as these precipitates dissolve, lowering the volume fraction, the rate of radii increase, that leads to a precipitous increase in the size of the ossified grains, typically resuming normal grain growth and stopping abnormal grain growth once there's a complete dissolution of those precipitates. So you can kind of see this demonstrated here in this work by Zhang et al. The temperature region of abnormal grain growth tends to decrease almost linearly with proportional reduction ratio up to about 50%. So here you can see normal grain growth, Tc, the temperature at which precipitates begin to dissolve, abnormal grain growth, and then Tf, where you typically have complete dissolution of precipitates and normal grain growth resumes. So you can see how that's affected by the amount of cold reduction done prior to heat treatment, and you can see this demonstrated even more clearly on these plots to the side, where the top is the alloy without any work done to it, and the bottom is with 50% cold reduction done to it, and you can see that temperature region where abnormal grain growth occurs just shifts to a lower temperature regime. So in work by Li et al., it was found that there's a correlation between cold work and abnormal grain growth in AISI 4121 steel and a niobium moly modified version of that steel. So these alloys can be seen at the bottom of the slide here. The most notable difference being the niobium content in the modified alloy, as well as having a lower aluminum and nitrogen content, because that's the primary precipitate for the standard alloy. So it's seeing the effects of precipitation from this microalloy. And you can actually see in the work by Li et al., the alloys were subjected to simulated carburization after some degree of cold reduction. Simulated carburization being carburizing temperature ranges just without a carburizing atmosphere. And you can see that at 10% cold reduction, there's a peak in the amount of abnormal grain growth and the prior arsenic grain size in general, and that's more prominent in the modified alloy than the standard. So due to the amount of warm work being integrated into processes prior to carburization, this work is investigating how that might affect abnormal grain growth. So these are the alloys utilized in this work. Again, the biggest difference being moly, niobium, aluminum, nitrogen content. These ingots were produced at Timken Steel via vacuum induction melting and subsequently forged at Solmet Technologies. So both these ingots that were produced were austenitized, forged into bars, and sheared into 5 separate pieces. And each of these pieces was set, one of these 5 was set aside, allowed to air cool after austenitization, and it was set as the as-forged condition. And the remaining 4 pieces were reheated to 900 C for some amount of cold reduction, ranging from 0 to 50%. So this is you have the initial bars after austenitization, which were sheared into 5 separate ingots. There were billets that were used for this work. So you can see the thermomechanical history of those as-forged ones that I mentioned. It was austenitized at 1230 C, allowed to air cool, and then at mines they were subjected to some degree of cold reduction, so either 0 where there's none, or 5, 10, and 25% cold reduction, and then subjected to simulated carburization for 0, 30, and 328 minutes. These times chosen because they were similar to work those used by Lee, and 328 in particular is typical for a carburization cycle. For the warm forged parts, they were heated, austenitized, allowed to air cool, but then brought up to 900 C and experienced some amount of warm reduction. So 0% being it was just brought up to temperature, didn't have any work done to it, and 5, 10, and 25% cold reduction were the other conditions used. So that was all done at Solmet, and then at mines, cold reduction and simulated carburization were performed. So to just give a layout of these experimental conditions we're using, you have the 2 alloys, the 5 different warm reduced conditions, including the as-forged condition, 4 different cold reductions, and 3 simulated carbonizing times. So we have a combination of each of these conditions in this work. So how the prior arsenite grain size is measured, used a MATLAB function to expedite the line intercept methodology. So the niobium modified alloy I'll refer to as 4121 niobium, and the standard alloy I'll refer to as 4121 aluminum, as you can see on this slide. And so this is the niobium modified alloy after 328 minutes at 1664. So X, and the way I did it, I clicked wherever the lines intersected with grain boundaries, and that gave me the intercept lengths. So I got a distribution for all of the grains within the samples I looked at. So the first results that we're looking at here are the effects of the initial microstructures. So we found that the alloys that experienced more warm work had a more refined microstructure prior to simulated carburization. So on the left are the initial microstructures. On the top, it's the standard alloy after no warm reduction, and on the bottom, it's after 50% warm reduction. So you can see clear refinement of the initial microstructure, and that led to a more refined prior arsenite grain size, likely due to the increasing of total grain boundary area and allowing austenite to nucleate at more sites. So a coarser grain, microstructure leads to a coarser prior arsenite grain size, and the same with the amount of refinement you see from warm reduction. Now, here's the standard alloy after 0% cold reduction. So this is just after, these are all the conditions with a warm reduction with no cold reduction done to it prior to that simulated carburization. This is representative of both alloys. They should both show refinement increases with an increased amount of work. And you can also see that the microstructures become coarser with increased hold time, which makes intuitive sense. But you can also see that abnormal grain growth is most prevalent in these conditions without a notable standout as far as what the data shows, and just looking visibly at the microstructures, seeing abnormal grains such as here or here. Now, as far as the measured results of the prior arsenite grain size, it's labeled as average intercept length because that's exactly what was directly measured, but this translates to prior arsenite grain size. And I have the as-forged condition sectioned off just because those initial microstructures were different due to the different cooling rates. The warm reduced parts were sealed together in a blanket and allowed to air cool much more slowly after their warm reduction, so their initial microstructures are different enough that I don't want you to be confused seeing them right next to each other. So you can see the effect of cold reduction leads to a less prominent refinement due to warm reduction. So this is true for any amount of cold reduction that we did, but this is just a good representative example. On the left, this is the standard alloy after Without any cold reduction, you can see it becomes more refined for all hold times as you increase the amount of warm reduction. And then after some amount of cold reduction done, you can see that effect is less prominent. It becomes more refined with the amount of work once you hit 50% warm reduction, but the effects of refinement are less prominent, particularly for the 328-minute condition. Now, looking at the effects of cold reduction, similarly, grain size is generally refined with the increase in cold reduction, likely due to an increase in the amount of deformation substructures and leading to more nucleation sites for austenite. And similar between both alloys, the previous slide being the standard alloy, this slide being niobate modified. As cold reduction increases, so too does the refinement of the microstructure. Now, these plots show the prior austenite grain size with respect to warm reduction, which is the scale on the bottom left, and with cold reduction on the bottom right. So you can see that prior austenite grain size between 0 and 328-minute hold times here generally increases with hold time, and after a small amount of work, the prior austenite grain size decreases acutely. So having this peak at 0% warm work, 0% cold work or reduction, and after either 10% warm reduction or 5% cold reduction, you have a prominent decrease in the prior austenite grain size. And you can also see that between the axes, the degree of refinement that you see from cold and warm reduction is roughly equal. There's not a huge distinction between the two across these plots. And this is true for the niobate modified alloy as well. But what you can notice is that rather than having a peak in the corner, it's more of a shelf at the 0% cold reduced condition. So the refinement is less prominent when there's no cold reduction with respect to warm reduction. So you can also see that, again, between the two, the 328-minute condition has a higher average prior austenite grain size. Now, comparing the effects of cold reduction on these warm reduced parts and those used observed by Lee et al., you can see that the trends are relatively similar, particularly for the 328-minute condition, which is the most relevant due to that being analogous to industrial conditions. So the no warm reduction are the plots by Lee here on the right, and I want to point out that the prior austenite grain size is finer in general due to the initial heat processing conditions done by Lee, where there was a 50% reduction, subcritical anneal, and then they were subjected to these measured degrees of reduction prior to simulated carburization. So you can see that in each of these plots, the prior austenite grain size for the 328-minute condition peaks at around 5 or 10% cold reduction, and between the standard alloy and the niobate modified alloy, there's a larger prior austenite grain size on average in the modified alloy. Now, regarding abnormal grain growth, any abnormal grains in this or Lee's work are defined as having a diameter equal to or greater than 30 microns. So the abnormal grain growth is normalized by the total grain area. So this is the total area of abnormal grains divided by the total area of grains measured in general, which we could do with the total measurement of intercepts of all the grains. So you can see that for shorter hold times, i.e. 0 minutes, abnormal grain growth is relatively proportional to the prior austenite grain size. So you have this peak in the back, and you have a decrease in abnormal grain growth with more work introduced into the alloy. And after 328 minutes, it becomes a little less similar, a little more all over the place. So you see less of a pattern of the abnormal grain growth after 328 minutes, but more in general. And for the modified alloy, similarly reflective after 0 minutes, you have that shelf along the right side, and abnormal grain growth after 328 minutes does not see as much of a sloping down with an increased amount of work. It's just generally a higher amount of abnormal grain growth across most conditions, and between any conditions of the standard alloy or the modified alloy, the 328 hold time of the modified alloy had the most amount of abnormal grain growth in general. So from what we found in this work, again, those initial microstructures we find vertic grain sizes due to the warm reduction correlate with a finer average pyrosinite grain size due to higher density nucleation sites. Both the pyrosinite grain size and the abnormal grain growth in 4121 and nitrogen modified 4121 generally peak at 0% warm reduction and cold reduction and decrease as work increases, with the exceptions of some 30 and 328 minute conditions. The pattern generally seen is just increased refinement. And between the refinement due to warm reduction and cold reduction, it's relatively equal. And of any of the conditions, the nitrogen modified alloy displays more overall abnormal grain growth after 328 minutes of simulated carburization than any other condition. That's all I have for you. I'd be happy to take any comments or questions.
Any questions? I have a question. So it was a simulation of carburization?
We refer to it as simulated carburization because it simulates the heat treatment without a carburizing atmosphere. So it's placed in a furnace at room temperature, heated 8 C per minute, and then left for whatever amount of time after you hit temperature. So not literally simulated.
What's the atmosphere that the parts are under?
Just air.
Just air.
Yeah.
Okay. Do you understand there's any decarb at that point when you remove those samples?
Yeah, there is decarburization, but all these are taken from far enough within the surface that you're not seeing that decarburization microstructure.
How big were the samples?
Maybe 5 millimeters, like 25 square millimeters.
Are there any other questions? Thank you very much.
Thank you.